All right, so let's take a more detailed look at energy-dispersive spectroscopy now, or EDS. So again, like I said, EDS is actually the second of the two chronologically, but it's been commercially available since the 70s, and I continue to have spelling struggles today. But it's been more popular than WDS because it has a more simple design, and that means less moving parts, and faster scans, and it can have what we call parallel detection. So not the sequential that we saw with WDS. However, like I mentioned with WDS, the resolution is worse. Worse resolution. And that tends to be on the order of 1.15 to 0.2 keV. So again, order of magnitude, we could get 0.01 keV for WDS. So that's definitely an improvement if you're talking about WDS. When we talk about when we talk about EDS, traditionally the more common detector historically has been this silicon lithium diode. And so this could only detect atomic numbers greater or equal to 8. So that's oxygen. However, there are newer what we call silicon drift detectors. So these are called SDD. So if you're looking at a product and you see SDD, that's silicon drift detector. So an example there is the Oxford X-ACT. And so this has been shown to detect as low as 4, which would be beryllium. So there's newer detectors out there that can go much lower than previously thought. There's even one Oxford detector that says that it can detect lithium, which is the 3rd atomic number. And so there's definitely advances that are still happening to this day with this technology. These detectors, these SDD detectors, they don't require liquid nitrogen like the older detectors. And so there's a fairly good part of this chapter on silicon lithium detectors in the book, but since they're really not as technologically commonplace compared to these newer ones, they're still around. But since the kind of technology has advanced, we're not going to kind of go into any more detail on like the mechanism for these detectors, because again, they're probably going to be eventually stopped using in favor of these other detectors. So if you want to know more, there's obviously a section in the book, but I'll leave it at that for now. Okay, so just like we did with WDS, I want to look at a typical spectrum that we would see in energy dispersive spectroscopy. So let me switch over and show you a typical spectrum. Okay, so this is a typical EDS spectrum. This is actually in our textbooks 6.10 and it's actually a spectrum of glass. So inorganic glass is silica, and also has other things like calcium oxide, aluminum oxide, iron, and barium oxides. And so this is what we're kind of expecting in this spectrum. So again, if we just kind of walk through this typical spectrum, a typical spectrum, we tend to run the detector and scan a certain level of energies. So in this case, the scan is from 0 to 10 keV, but another common range would be 0 to 20, and so forth. It really depends on what you want to detect and how long it's going to take. And so here we see that again, energy is increasing on the bottom. If we were to plot it, the wavelength would go in the opposite direction, and then this is intensity of or counts of these X-rays that we detect. And so what we see is that we see the K lines, a lot of K lines here, particularly of the lighter elements, because those energies are small. And then we see the L or M lines, so a lot of M lines, a lot of L lines for those that are heavier, because those tend to be smaller. So we don't have to run the energy super high, because we can detect the L and M lines of the heavier elements at the lighter, at the lower energy levels. So that's one reason why a lot of times we won't go above 20. So barium, for example, is a relatively heavy, and so the L lines are what you see. To get the K lines, you'd have to go much higher. You might also notice that what we call the signal to noise, so one of these peaks would be referred to as the signal, and then the noise is just the sort of ambient level of background radiation that we detect. And so the signal to noise is relatively low compared to what we saw in WDS. And so the peaks sometimes don't rise above the background super well. And so again, that kind of lends itself to the sensitivity of this compared to WDS. So early EDSs, definitely had problems with not enough photons emitted from the spectrum and reaching it to the detector. And so one way in which we can get around this is by a concept one thing connected to this is what we refer to as the dead time. So let me switch over and write this out for you. All right, so due to the design of these detectors, if we emit too many X-rays to the detector basically gets saturated, and so we can't detect more and more X-rays. And so there, in fact, is a period during which the detector can't detect. Correctly. So because of that problem with the detectors, we have this issue, and it's called dead time. So when you're using an EDS, particularly the most common one that you're going to use is with an SEM, and this is where electrons are the incident beam, but the concept is the same. The dead time is something that you might see when you're dealing with the EDS software. And so this is basically the time at which the detector can't respond to more photons correctly. And so this is in the order of 0.5 times 10 to the minus 7 seconds. So this seems like a short time, but it still causes some issues. So this is with the older detectors. The SDD ones are much better at this case. And so the limitation that causes is that there's a maximum count rate that we can detect, and that is in the order of 3 to 4 100,000 counts per second. So CPS means counts per second. And this leads to 100,000 to 200,000 total counts in a typical 1 minute acquisition time. So this dead time limits how much overall counts we can actually detect. And again, this is one of the situations where the SDD detectors increases this overall number of counts, and so we can get as many as 100,000 or hundreds of thousands of counts per second. So again, it's a huge difference, and it allows us to do some different things like live spectral imaging, which you can't do if you have these kind of dead times.